طيب السلام عليكم شباب. إن شاء الله today we will start إن شاء الله chapter 3. Last time we end up with chapter 2. We have learned how to write down to develop the first law equation for the first law of thermodynamic equation for open system and for closed system. And inshallah we said we have stopped at this stage, and inshallah we will learn in chapter 3 how to calculate the properties that we have seen in the first law form, properties like internal energy, enthalpy, specific volume. All of these properties inshallah we will learn how to calculate for the different substance. Then inshallah we'll get back in chapter 4 and apply this equation and solve some problem inshallah. طيب, chapter 3 is properties of pure substance, how to calculate the properties of pure substance. Inshallah, in this chapter we'll introduce to the concept of pure substance, its definition, what does it mean actually pure substance. Then we will discuss the phase change process. We will represent actually the phase change process from the liquid phase to the vapor phase, especially for water. We represent actually this process on the PV diagram, on the TV diagram, and also in the pressure. PV is the pressure specific volume, TV is the temperature specific volume, and BT is the pressure temperature diagram. Then inshallah we'll represent the whole process on the 3D surface PVT diagram for the phase change process. Inshallah we'll be mainly focusing on water, the phase change of water to generate steam. Steam is used actually in a steam power plant for electrical power generation. So usually we burn the fuel to generate heat. Then we use this heat actually to boil the water to generate steam at high pressure and high temperature. Then we pass this steam actually to the turbine. Part of the turbine is nozzle to accelerate the flow with high velocity jet. Then this high velocity jet can hit actually the blades of the turbine. Then we can have mechanical shaft power. This mechanical shaft power can be simply connected to an electric generator. Then we can generate electrical power, and this is actually called as gas turbine for electrical power, steam turbine, sorry, for electrical power generation. So we are mainly concerned here actually with the properties of steam at different conditions. Because actually of its mainly application for electrical power generation. So inshallah we'll demonstrate the procedure how to calculate actually the thermodynamic properties. We said we can specify the state of a substance using two independent and intensive properties. Like let's say we have pressure and a specific volume, steam with a given pressure and a given specific volume. Then actually we can use the steam table to calculate actually all of the other properties in terms actually of internal energy, enthalpy, entropy. All of the other properties can be calculated in this case using two independent and intensive property. So inshallah, after learning how to use a steam table to calculate the properties, we'll be moving inshallah to the case of ideal gas. Ideal gas actually is a state actually of the gas. We can consider any gas as an ideal gas actually under very low pressure and high temperature or very low density. And in this case, we can apply properly actually the ideal gas equation of a state. I think you have an idea about which state actually PV is equal to mRT. So if we have pressure and volume, then we can calculate the temperature using the ideal gas equation of a state. But as I said, this equation actually can only be applied for a gas under ideal condition, which is actually the condition of very low density or very low pressure and high temperature. Then this equation will be correct. Otherwise, actually, this equation has to be modified for the real situation, for the case of real gas. And in this case, inshallah, we'll introduce what's called the compressibility factor. We will modify this ideal gas equation, and instead of PV equal to mRT, it will be PV equal to compressibility factor, we call it Z, multiplied by M, multiplied by R, multiplied by T. Then in this case, actually, inshallah, we'll look at this compressibility factor and how we can calculate it so that we can apply this ideal gas equation of a state. It can be applied actually at any condition of the gas for the real gas as well. Also, we'll look inshallah in this chapter, we have some modification for the ideal gas equation of a state to be applied for the real gas. Inshallah, we'll look at actually some of this equation based on modification actually for ideal gas equation. We'll look at them inshallah and we'll solve inshallah some problem. So inshallah, mainly in this chapter we are concerned to calculate the properties of steam using steam table. Also, we are concerned mainly to calculate the properties of the gases either actually using the ideal gas equation of a state if the density of the gas is low, or actually the modified equation, ideal gas equation of a state, inshallah, using the compressibility factor, and we will look at them, inshallah, later on. Type the definition of pure substance. Pure substance actually is a substance of fixed chemical composition. So this substance has actually fixed chemical composition everywhere. If we have single substance like nitrogen, then in this case, this is a pure substance, same N2. This actually concentration or chemical composition is the same everywhere, so we can call nitrogen as pure substance. But what about air? Air is a mixture of oxygen plus nitrogen plus some other component. But actually, as long as actually we have the same chemical composition and we have the same concentration of the air everywhere, that means actually this represent a homogeneous matter. Then in this case, with the same chemical composition everywhere, then in this case actually air is considered as also as a pure substance. What about if we have water, liquid plus vapor water? As long as we have the same chemical composition, the same substance, H2O is the chemical composition, everywhere is the same, either liquid or vapor phase, then in this case, when we have a mixture of liquid plus vapor water within the same system, then we can consider this system actually as a pure substance as well. What about if we have air plus liquid? In this case, actually air, let's say air plus liquid water. Then in this case, actually, they have different chemical compositions. Then in this case, we cannot say this mixture represents actually a pure substance. So pure substance can be single substance, can be mixture if we have the same chemical composition everywhere. It could be actually a mixture of liquid plus vapor of the same substance, but actually it cannot be actually a mixture of air plus liquid of different actually chemical composition. Okay, so the condition for the pure substance is to have actually fixed chemical composition everywhere. The substance actually pure substance can exist in mainly in three phases. It can either exist in the solid phase, or it can exist actually in the liquid phase, or it can exist actually in the case of vapor phase. This is actually a 3D lattice structure of a solid substance. As you see here, the molecules are connected in a spring-like connection, spring-like connection. And actually, the attractive and the repulsive forces between each molecules actually just keep those each molecule in its position. So actually, the movement of the molecule in case of the solid substance are almost not existing. We don't have molecular movement in this case. In case actually of liquid fuel, in case actually of liquid substance, in this case actually the intermolecular force is just actually being reduced as compared to the solid phase, and the molecules are actually allowed to move in this case. In case of vapor substance, or in case of the gaseous phase, in this case actually we don't have any molecular order, and the molecules actually have the full freedom to move. And actually, depending on the pressure and temperature of a substance, it can exist actually either in the solid phase, liquid phase, or in the vapor phase. So at room temperature, 25 degrees C or something, copper is a solid substance, mercury is liquid, and we have nitrogen actually is a gas. But if we raise the temperature, then in this case, this copper actually may be melted to the liquid state at different temperature, at higher temperature. And this liquid mercury can be converted to the vapor phase. So depending on actually pressure, temperature, we can have actually a substance either in the solid, in the liquid, or in the vapor phase. And we have another phase which is called the plasma, but we are not actually here in this situation to talk about it. So let's consider we have three main phases: solid, liquid, and the vapor phase. As I told you, inshallah, in this chapter we are mainly concerned with the steam table. So we'll look, inshallah, look at actually the properties of steam at any given, actually two given independent and intensive property. We'll learn, inshallah, how to calculate the properties of steam. But let's look first of all about the phase change process for pure water. So let's say we have water existing at the liquid phase, and we need to look at actually the saturation curve or the phase change process from the liquid phase to the vapor phase. So let's say we have water in a tank in a piston cylinder device. This is actually water. existing at temperature, room temperature equal to 25 degrees C. This piston is free to move. Then in this case, this is actually free to move. So that means actually when we add heat here, if heat is added, then in this case actually this piston, as it is free to move, the water will expand in this case, and the pressure in this case will be remaining constant. The pressure in this case is equal to the atmospheric pressure. Okay. So let's say actually this is the state number 1. At state number 1, the temperature of the water is equal to 25 degrees C, and in this case actually the pressure is equal to 1 atmospheric. And the state of water in this case at atmospheric pressure, temperature is equal to 25 degrees C. That means we have liquid water. So it is called actually as subcooled. The state of water is called as subcooled, or we call it actually as compressed liquid in this case. Okay. Let's look at this process of phase change on the phase change diagram on the temperature specific volume diagram. So usually temperature will be in Kelvin and the specific volume is in meter cube per kilogram. And let's represent this state number 1 on this curve. Let's say actually this is state number 1. Start boiling this water. Let's add some heat. So adding some heat will result actually in temperature rise. Okay. Then in this case actually the temperature will be raised. Let's continue adding heat. This heat actually is called the sensible heat. Sensible heat is the heat added, and actually is the heat added as that result actually in a temperature rise. So in this case the temperature will be raised in this case. Continue adding the heat actually until we reach state number 2, at which actually the temperature is equal to 100 degrees C. So under atmospheric pressure and temperature equal to 100 degrees C, that means actually the water will start boiling. But it did not actually start boiling. It will start boiling if we add any more amount of heat. So at state number 2, at which the temperature equal to 100 degrees C, we call this temperature actually as the boiling temperature or saturation temperature, Tsat. Tsat means the saturation temperature, which is the temperature at which we have phase change at a given pressure. In this case, the given pressure is equal to 1 atmosphere. So at 1 atmosphere, the boiling temperature of water or the saturation temperature at which we can have phase change equal to 100 degrees in this case. At point number 2 or state number 2, at this state actually the temperature is equal to, we call it as Tsat, the saturation temperature, which will equal to in this case 100 degrees C. And the pressure in this case, which is 1 atmosphere, we call it as the saturation pressure, which is the pressure at which we have phase change at a given temperature. Okay, so this is called as actually as the saturation pressure, which is fixed in this case, equal to 1 atmosphere. Okay, and the state of the water in this case is called as saturated liquid. So the state of water is called as actually as saturated liquid in this case, and all the properties of the water at this state has actually the subscript F. F indicates fluid. So in this case, this is the TV diagram. So the specific volume, we'll call it V fluid. The internal energy, we'll call it actually specific internal energy, we'll call it U fluid. We have the subscript F indicating the saturated liquid state. In Sulby, we'll call it H fluid. And also the entropy, we'll call it S fluid. So all the properties at state number 2 are the saturated liquid properties. So those properties are actually saturated liquid properties. Okay, all the properties we call them actually VF, which is the saturated liquid specific volume, saturated liquid properties, internal energy U fluid, and Sulby H fluid, and the entropy is S fluid. And this state actually we call it the state actually of saturated liquid. Saturated liquid, which is the liquid that is actually about to vaporize. If we do what? If we added any amount of heat, then in this case actually some liquid would be converted to vapor. But if we added some heat, then in this case will the temperature rise? No, the temperature will not rise in this case. In this case, the heat added after state number 2 is called as actually latent heat. Latent heat is the heat actually that results in phase change, not temperature rise. So the heat added from state 1 to state number 2 is called the sensible heat. because it results in temperature rise. Once we reach the saturation or the boiling temperature, when we add more heat, the temperature will be fixed at the saturation temperature. But what will happen, this amount of heat is going where? Is used actually to convert some liquid, the water from the liquid state, convert some water from the liquid state actually to the vapor state. Okay, but in this case actually the temperature will be remaining constant. Let's say here actually we are at state 3. At state number 3, in this case we have a mixture of liquid plus vapor, and we call this is actually a pure substance as long as we have the same chemical composition. So at state number 3, in this case actually the temperature is the same, equal to the saturation temperature, which is equal to 100 degrees C. Pressure is the saturation pressure, which is equal to actually the atmospheric pressure, which is equal to 1 atmosphere. And in this case, the state of the substance, we call it actually, we have saturated mixture of liquid plus vapor. So we have saturated liquid plus vapor mixture in this case. Okay, so at state number 3, we have a mixture of liquid plus vapor, and the state is called as actually saturated liquid plus vapor, saturated liquid plus vapor mixture. But at this state actually, how we can define actually the state of this mixture? So we can define the state of this mixture using actually what we call the quality of this mixture. So we have a parameter x. This parameter x, which is called actually the quality of the mixture. So the mixture is defined actually using the quality of this mixture, which has the symbol x. The quality of the mixture is the ratio between the mass of vapor, we call it mg. G indicates actually the gas phase. So the mass of gas divided by the total mass, which is mass of fluid, mf plus mg. And the quality of the mixture, this parameter actually has a value x is greater than or equal to 0 and less than or equal to 1. When this x is equal to 0, when we actually the mass of gas is equal to 0. At which state? At state number 2. So at state number 2, the quality of the mixture x is equal to 0, because actually we have saturated liquid. We don't have any gas at state number 2. When we start adding heat after state number 2, then in this case some gas will be formed in this case. So the value of the quality of the mixture x, this parameter, is equal to 0 at state number 2. So what about at state number 3? We have a mixture of liquid plus vapor. So in this case we have gas, mass of gas plus mass of fluid. So its value will be greater than 0 and less than 1 in this case. Okay. Like what will happen actually if we continue adding heat here after state number 3? If we continue adding heat, in this case all of the liquid will be converted to vapor at a given state. Let's say this state actually is state number 4. At state number 4, we call it actually the saturated vapor state. And in this case, all of the properties, the specific volume, we'll call it Vg, indicating actually the gas phase. So this is the saturated vapor specific volume, Vg. Vf is the saturated liquid specific volume. Like this, the internal energy will be U gas and some H gas. In this case, also the entropy will be S gas. By saturated vapor at state number 4, all of the liquid has been converted to vapor. So we don't have fluid, so mass fluid will equal to 0, and the quality will equal to mass of gas divided by mass of gas. In this case, the quality of the mixture, we call it actually x is equal to 1 in this case. And in between state number 2 and state number 4, x will be greater than 0 and less than 1 in this case. And we call this actually as the quality of the mixture. So at state, let's write down this. If you are writing behind me, and I would prefer if you do. So at state number 4, in this case actually, we have saturated. So at state 4, in this case actually the same temperature is equal to the saturation temperature, equal to 100 degrees C, and the pressure is equal to B atmospheric, is fixed. Okay, And in this case, actually, the state of the substance is saturated vapor in this case. We call state number 4 as saturated vapor. And in this case, at state number 4, we get back actually to the single phase. We don't have double phase in this case. So what will happen if we added more heat to the water? We said we have a water. Remember, this is the water in a piston cylinder device. And we are adding heat here. At state number 4, it is actually single phase. Now it has been converted from the liquid phase to the vapor phase. As long as we have single phase, we don't have phase change. Then in this case, if you continue adding heat at state number 4, now the temperature will start rising again until we reach actually, let's say, state number 5. So at state number 5, in this case, actually, the temperature will be greater than what? The saturation temperature. This line represents fixed saturation temperature and fixed saturation pressure. From state 2 to state number 4, temperature is the same, T saturation, pressure is the same, B saturation. Okay? But at state number 5, in this case, the temperature will be higher than actually the saturation temperature. So at state number 5, T is greater than the saturation temperature. At the same pressure, this phase change process is done at fixed pressure. So all of this point from 1, 2, 3, 4, 5, all of the points are at the same pressure. So this line represents a constant pressure line on the PV diagram. And the state of the substance in this case actually is called as superheated steam. So in this case, at state number 5, the steam is at a state, we call it actually as superheated steam. Okay? If we heat up from state 1, we can reach a state actually up to state number 5. If we reverse cool down at a constant pressure, and instead of heating up, if we are cooling down, then in this case, we will do the same. The gas is superheated vapor. When we cool it down, it will reach first saturated vapor. Then if you continue cooling, then we will have mixture. Continue cooling, then you have the saturated liquid state. If you continue cooling in this case, then actually the substance will be converted to liquid back. The heat added from state number 1 to state number 2 is called the sensible heat because it results in temperature rise. Like also the case from 4 to 5. This is sensible heat because we have temperature rise. But the heat added from state 2 to state 4 is called the latent heat. We call it actually as latent heat of vaporization. So when we add heat from 2 to 4, this is called actually latent heat of vaporization, which is the amount of heat added to convert the substance from the saturated liquid phase to the saturated vapor state. Type if we reverse and cool down from 4 to 2, the same actually if you reject the heat, in this case actually the same amount of heat action. But if you are cooling down, we call this heat actually as latent heat of condensation in this case, not vaporization. But actually latent heat of condensation while cooling is exactly same value. It is actually the same value, the same amount of heat for vaporization to convert from the liquid phase to the vapor phase. So we have latent heat of vaporization from the liquid to the vapor. We have latent heat of condensation from the vapor to liquid, and they are equal. Also, we have latent heat of fusion or melting, which is the amount of heat added to convert the phase from the solid phase to the liquid phase. It is called also as latent heat of melting or fusion. We call it latent heat of fusion from the solid phase to the liquid phase. Saturated solid to saturated liquid. Also, it is the same or equal to actually the latent heat of freezing to convert from the liquid phase to the solid phase. So the latent heat of freezing from saturated liquid to saturated solid is the same actually latent heat of fusion from the solid to the liquid. Okay, so we have actually in this case latent heat is the heat actually while supplied or rejected, added or rejected while the phase change process. Those are actually the parameter we said. طيب, what will happen يا شباب if we raised the pressure? Okay, so we said in this process we are adding heat here. In this case actually the pressure is atmospheric pressure. So we said this piston is free to move, and in this case actually If we added heat, the piston will be moving and the pressure will be kept the same. طيب if I added يعني loads to this piston, in this case I will raise the pressure. Then I can repeat the same process under fixed pressure, but higher pressure in this case. So this is the tank, the piston cylinder valve. This piston is free to move, and in this case we have water. If we added some weights here, then in this case the pressure of the water will be raised, in this case higher than the atmospheric. Then we can fix the weight, the pressure will be fixed. The same pressure will be constant in this case, but it will be higher than the atmospheric pressure. Then we can add heat here and look at actually the phase exchange process. So what will happen to this saturation curve from the saturated liquid to the saturated vapor phase? Let's discuss here يعني some few points and then we can move. Here actually what will happen if you look here, actually what happened to the saturation pressure or the saturation temperature. If the pressure is raised actually, then the saturation temperature or the temperature at which we have phase change or boiling temperature will be raised in this case. So look here for the case of water. Water actually at 100 kilopascal, water boils actually at 100 degrees C. But if I raise the pressure of water, let's say 5 times atmospheric pressure, then in this case, if I raise the pressure, the temperature at which we have phase change or the boiling temperature, we call it saturation temperature as well. In this case, actually, this temperature will be raised. So as we increase the pressure, then in this case, actually, the saturation temperature or the temperature at which we have phase change will be raised in this case. And this is the idea, Shabab, of the pressurized cooking vessel. So the idea of the pressurized cooking vessel is actually to increase the pressure. Then in this case, the boiling temperature at which we have the food is boiling. Usually the food, most of it is water. So usually the food, any food will be boiling very close to 100 degrees C. So if I raise the pressure inside this high pressure or pressurized vessel, cooking vessel, then in this case, the temperature at which the boiling occurs actually will be raised in this case. That means we have to add, the food will be absorbing more heat until it reaches actually this high temperature under high pressure to have the phase change process. That means actually the food will be cooked faster and very well in this case, because we have raised the temperature at which we have phase change. That means we have to add more heat until we reach this temperature. More heat added to the food, that means actually it will be cooked faster in this case. And this is the idea of the pressurized cooking vessel. You have to have one. So here also, as you know, in the atmosphere, as we go at higher altitude, in this case, actually the atmospheric pressure is reduced. So at sea level, the atmospheric pressure is 100 kilopascal and the boiling temperature is 100 degrees C. But if we go higher altitude, in this case, as we get higher, in this case, the atmospheric pressure get reduced. Reducing the pressure, that will reduce actually the temperature at which we have phase change or the boiling temperature. So usually in civil aviation, if you are inside an airplane, usually airplane actually are flying at a height equal to 10,000 meter or 10 kilometer. So in this case, actually the temperature, the pressure, the atmospheric pressure outside the airplane in this case will be about 26.5. That means the water outside the airplane, if you have your hand and you are able to get your hand outside and boil water, in this case the water will be boiling at 66.3, but not inside the airplane, because inside the airplane usually the pressure is adjusted to the atmospheric one, okay? But outside the airplane flying at 10k meter, it will be actually, the temperature will be 66.3. Those are the latent heat as we have defined, the heat actually to have phase change. For water at atmospheric pressure, the latent heat of fusion to convert from the solid, from ice to water, it is equal to 333.7 kilojoule per kilogram. But the latent heat of vaporization to convert from the liquid to vapor phase is equal to actually 2,256.5 kilojoule per kilogram. This is just an example. But let's get back here to our point. So what will happen? We have seen actually the phase change process here. We have seen here, this is actually the saturation curve. If the pressure is equal to atmospheric pressure, in this case, the saturation temperature will equal to 100 degrees C. But we said if we raise the pressure, in this case, if we add more loads here, then we can raise the pressure. Then if we add heat under this fixed pressure, then in this case, we said the saturation temperature in this case should be higher. So if we repeat the process again, then we can get actually another saturation curve here. State point number 1, point number 2, point number 3 mixture, point 4 saturated vapor, and then we can reach point number 5 in this case. And in this case, actually, the saturation temperature at the new given pressure will be raised in this case, because as the pressure increases, the saturation or the boiling temperature will be increased. And also, the volume, specific volume difference between saturated liquid and saturated vapor will get actually reduced, because increasing the pressure will reduce the volume, okay, for the same mass. So in this case, this difference between V fluid and V gas will be reduced. But if I repeat the process at higher pressure, then in this case we can get this curve. Until actually we reach a point, we call it actually the critical point. This is actually the critical point. The critical point at which is the pressure is B critical, and the temperature in this case actually we call it the critical temperature. And the critical point is the point at which actually we do have the saturated liquid vapor, the saturated liquid state, and the saturated vapor states are identical. They are actually only one point, okay? And in this case actually, if we just connected those points, saturated liquid point, then we can get actually the saturated liquid line. This is actually the saturated liquid line. Throughout this line, the value of the quality of the mixture X is equal to 0. All of these points are actually the saturated liquid point. We can connect also the point of saturated vapor. So this line represents actually the saturated vapor line. Through this line, the value of the quality X should equal to 1 in this case. Okay. And actually, to the left-hand side actually of this saturated liquid line, in this zone, the state of the substance, we call it actually, as we said, subcooled or compressed liquid substance. So the substance in this case to the left-hand side of the saturated liquid line, this line is called actually subcooled. The state of the substance is subcooled or compressed liquid. But between the saturated liquid and saturated vapor line, we do have saturated liquid plus vapor mixture. So this zone we have saturated liquid plus vapor mixture. We have mixture of liquid plus vapor between the two saturation lines. But to the right hand side in this zone actually of the saturated vapor line, in this zone actually the state of the substance, we call it actually as superheated zone. Superheated zone. In this zone actually the state actually of steam is in the superheated state. And that's why for steam table, inshallah we'll learn the steam table, how to calculate the properties. We will see we have three tables. One table for the subcooled region, in which actually the temperature in this zone for the subcooled is less than the saturation, less than the boiling temperature. So still it is actually water or liquid water. Right. We'll have a table for the subcooled region. In case when we have a mixture, then in this case we have another table for the saturated liquid plus vapor mixture. And for the third zone here, superheated zone, in this zone actually the temperature is greater than the saturation temperature. We will have actually a third table. But for the saturated liquid plus vapor zone, in this zone actually the temperature, as we said, the temperature is equal to the saturation temperature, and the pressure is equal to the saturation pressure. And the value of X is greater than 0 and less than 1. It is equal to 0 at the saturated liquid, and it is equal to 1 at the saturated vapor state. Okay, we can represent this process also on the BV diagram. This is TV diagram. On the BV diagram, it will be much simpler. Yani. We can get the same curve at different pressure. We can repeat the process, and you can get actually this saturation curve. So on the BV diagram, as we said, point 1, 2, 3, 4, 5 are at the same pressure. This actually is the phase change process, and that is done under constant pressure. On the BV diagram, line of constant pressure will be just a horizontal line. So this is state number 1, if you add heat actually. So if you look at state number 1, the temperature line on the PV diagram, this line represents the constant temperature line. In this case, the temperature is less than the saturation temperature, okay, at point 1. But if we continue adding heat, then in this case we can reach the saturated liquid state, and the temperature in this case at point number 2 is actually the saturation temperature on this line. This T is equal to the saturation temperature, line of constant saturation temperature. From state 2 up to state 3, when we have mixture until we reach state number 4. From state 2, 3, 4, we have the pressure is the same from 2 to 4. Temperature is the same, which is T saturation. If we continue adding heat at state number 4, then in this case we can reach state number 5. At state number 5, this is actually the line of constant temperature on the PV diagram. In this case, actually, the temperature at state number 5 is greater than the saturation temperature. Be careful, Shabab, about the representation of PV and TV diagram, because inshallah, in any problem, you will be asked to represent the process on the PV diagram and also on the TV diagram. By this, we are done today with today's class. So inshallah, let's continue inshallah next time.